Good morning. I can't believe we're actually at lesson 6 already. This is going to be quite a short lesson because once you've done this lesson, we're done with bonding and the shapes of the molecules. And before we can go on with intermolecular forces, you need to understand all of this very well. So when you're done with today's short lesson, please go back and look at everything up to this point because you must understand everything up to this point very well before you can move on. So for the giant molecules, if you look at the elements that they're made of, silicon is in group 4. So, and you know it's a non-metal. So silicon is a non-metal. Oxygen is also a non-metal. So if you think back for covalent bonding, it's always going to be two non-metals combining with each other. So it's still covalent bonds, and that is super important that you need to know here. It is still covalent structures, and these bonds are intramolecular bonds. So they're between the atoms still. So if you look at the bond here between that silicon and oxygen atom there, remember bonds are only between two atoms at a time. If you look at that bond there, it's a strong covalent bond. They're sharing electrons, those orbitals are overlapping, and it forms a strong covalent bond. Now, if you look at this molecule, it doesn't form small molecules like when we saw with carbon dioxide where we have CO2, and that's my whole molecule. These molecules, these are called simple molecules, and those are the ones we've looked at already. So they're not like that. They are huge molecules, okay, relatively huge molecules, because they contain a lot of atoms. Now, we don't expect you to know the cut-off point. You need to know that these three substances are form giant molecules. So it's silicon dioxide, diamond, and graphite that will always form giant molecules. So the other one, if you look at diamond, so the whole thing is one molecule. If you look at diamond, diamond is carbon and carbon. So still carbon and carbon and then carbon and then carbon, and it carries on like that. So again, it's a non-metal and a non-metal. And because it's two, so non-metal atom, so it's pure covalent or non-polar covalent bonds between these two atoms here. And that's how they carry on in a diamond. So you don't form small molecules again, and the whole thing is one big molecule. So if you want to melt a diamond, you have to actually break those intramolecular forces, and those strong intramolecular forces with the orbitals overlapping are very hard to break, and therefore you will need a very, very high temperature to overcome those forces. Graphite is a little bit special. Sorry. It is also a giant molecule, but if you look at graphite, there are layers within the graphite. Graphite is still carbon, so it's carbon and carbon and carbon. So in these layers, you have carbon atoms bonding with each other. So that would be my one giant molecule. The one layer is the one giant molecule. The next layer is my next giant molecule, and the next layer is my next giant molecule. So within these layers here, you can see there between the there, and there, where I'm making the dots. Those are the strong covalent intramolecular forces, still pure covalent or non-polar covalent because it's carbon and carbon, but those are strong. So if I want to melt again graphite, what happens is, what I have to do is I have to break these atoms apart. And to break them apart, I again need a lot of energy. So they will have a very high melting point and a very high boiling point. All three of these giant molecules will have high melting points and boiling points because you have to add a lot of energy to break those atoms apart. But now the only difference here with graphite to the other ones is that here in between these layers, there are not such big forces, and those forces we're going to look at in the next bit. They are called intermolecular forces, and those forces are relatively weak. Now, I think all of you know that graphite is what a pencil is made up of. So in graphite, these layers here can then slide over each other because those forces are not so big. And because they can slide over each other, the one layer of your pencil is basically sliding onto your page. And that's how you can write with a pencil, even though the forces are actually quite strong. Then the last type of bonding we have to look at is metallic bonding. Metallic bonding should be very easy to spot because it's only in metals. So you will have a metal and a metal atom, and it can be the same metal atom. Most of the time it is the same metal. Because if you look inside a metal, now I'm going to just give myself a clean space here to write. If you look inside a metal, what happens is, what happens is you've got your positive nucleus. You all know now that this positive nucleus is surrounded by energy levels and electrons and orbitals. Now for a metal, metals are very dense, so these particles are very closely packed. So the next nucleus will be close to that nucleus. Sorry. So what's going to happen is the orbitals of this one that will be the same as the other one. So if the other one had two energy levels, this one will have two energy levels as well. But the metals are quite low in the periodic table, so they will have more than that even. So what happens, like you can see here, is that if I had an electron here in this energy level, so I have electrons there in the outside energy level, and you should remember that we call them valence electrons. These electrons, when they now move in their orbitals, because of these orbitals also overlapping, they can move from the one atom to the next. And that happens throughout the metal. So electrons in a metal are free to move. And that is why metals are good conductors of electricity, whether they are solid or a liquid, doesn't matter, because these electrons are free to move. So what we call these, or these are just a nucleus and a nucleus. So the particles in a metal is still a nucleus, the positive nucleus, surrounded by its electrons. So it's a positive nucleus that's basically kept together by the delocalized, we call them delocalized electrons because they don't belong to one atom at a time. So they delocalized electrons, and some books will call them a sea of electrons. And these electrons then can move around, conduct electricity, conduct heat, and that is why metals are seen as good conductors. So if we look at your notes, that's exactly what they are showing you here. So you can see here that there are positive nuclei, and then those valence electrons on the outside can move, and that, like I said before, they call them a sea of delocalized electrons. But I want you to quickly focus on the particles here. Particles is just a general name. You're a particle, I'm a particle, an atom is a particle, an ion is a particle. So it's just a general name that we use for atoms, ions, molecules, and all those things. So everything is a particle. We've discussed this in class already. So now what you need to focus on, because it's important for the next section, is when we look at the different types of bonding, metallic bonds. So if you look at this summary of the particles, if you have discrete molecules, remember, we actually called them simple molecules. So discrete, you can rather use the word simple. Okay, so for the simple molecules, those are the small molecules like CO2 and so forth. What you're going to have, if you have a discrete molecule, then the molecules the molecules are going to, why it says atoms of noble gases, because remember, atoms of noble gases do not form molecules. They stay atoms because they don't want to combine. So they are never going to conduct electricity. If we have covalent bonds, giant structure, the particles are atoms. So covalent bonds, the particles are atoms. What I really wanted to say here and this is what we need to say here. This is for covalent substances also. The particles are called molecules. For giant structures, the particles are still atoms. For ionic substances, the particles are ions. And for metallic substances, the particles are positive ions, or you can say positive nuclei, and you'll see some textbooks call them positive kernels, and then they have delocalized electrons around them. I actually want you to scratch out the word ions and just say positive nucleus and delocalized electrons. So please, all of you, I want you to scratch out ions there because we don't call them ions. For the metallic bonding, scratch out ions and write nucleus. Okay, please, that should be that. And so for metallic bonds, we also don't form molecules. So the main thing I want you to see from this page, and that you need to know, and it's very important for the next section, is the only one of these that form molecules. So to form a molecule, it has to be a covalent bond. So if it's an ionic bond or a metallic bond, it does not form a molecule. Covalent bonds are the only ones that will form molecules, and they are the only ones that can take us then to the next part. We're going to look at intermolecular forces. Alright, so that's that for today. But like I said, please, you have to do the exercise that it tells you in the lesson, and also go and re-look at everything, because before you go on to intermolecular forces, you have to understand everything up to page 221, actually 222, very well.